Hey everyone, and welcome to this explainer. Today, we're going to totally demystify the hidden chaos that's operating just out of sight right inside our computers. You know what, we rely on our machines to be these perfectly logical, absolutely flawless boxes, right? But honestly, when we pull back the curtain on how multiple processes actually share memory, things get incredibly messy very quickly. We're going to explore exactly how and why that happens, and more importantly, how computer science actually solves it.
Okay, let's dive into this. Before we get into the microscopic code, let's look at a remarkably relatable real-world example just to set the stage. This is known as the too much milk problem. Imagine two roommates, let's just call them roommate A and roommate B. They both arrive home around the exact same time and they both notice a glaring issue. The fridge is completely out of milk. So here is exactly how this human error unfolds. Roommate A opens the fridge, sees no milk, and immediately leaves for the grocery store. 10 minutes later, roommate B opens that exact same fridge, sees no milk, and also heads to the store. Because they didn't communicate, they both act on the exact same completely outdated, shared information. And the result, they both buy milk, come home, and now you have an inconsistent state. Way too much milk. They relied on a shared resource, the fridge, without any synchronization. Now, that's just a funny misunderstanding in a kitchen. But what actually happens when we transition this exact same logical flaw into the heart of your computer?
Section 1. The microscopic zoom. We are dropping down to the CPU level.
Take a look at this deceptively simple command, x equals x plus 1. It is basically the most basic piece of logic you could write. Take a variable and increment it by 1. Now, let's assume our shared variable x starts with a value of 50. What do you think happens if two completely different threads, say thread 1 and thread 2, try to execute this exact same line of code simultaneously on that shared variable?
Well, naturally, if x starts at 50 and two threads both add 1 to it, our basic math skills tell us we expect a result of 52, right? 50 plus 1 plus 1. But here's the crazy mystery. Sometimes the computer spits out an actual result of 51. The computer literally loses an entire command. Why does that happen?
Now, what's really interesting about this slide is the illusion of high-level code. To you and me, x equals x plus 1 looks like a single, unbreakable atomic operation. But the CPU, it doesn't see one command. Down at the assembly level, it actually requires 3 separate physical steps. First, the CPU has to load the value of x from shared memory into a local register. Second, it has to add 1 to that register value. And finally, it has to store that newly calculated value right back into the shared memory.
Section 2. Visualizing the collision. This is what happens when assembly instructions overlap.
Because these 3 distinct assembly steps take physical time to execute, a massive vulnerability opens up. When 2 threads are running concurrently, the operating system can dangerously interleave these micro-instructions. They overlap, literally just like our roommates heading to the store at slightly different times. Let's do a play-by-play narrative of this collision. Thread 1 steps up and loads the variable. It sees a 50. But before thread 1 can actually do the math, boom, a context switch happens and thread 2 jumps in. Thread 2 also loads the variable from memory. Since thread 1 hasn't updated anything yet, thread 2 also sees an outdated 50. Now, thread 1 adds 1 to its local register, getting 51. Thread 2 adds 1 to its local register, also getting 51. Thread 1 finally stores its 51 back to shared memory, and literally a microsecond later, thread 2 overwrites that memory by storing its own 51.
So, the crucial point is that whoever stores their data last wins. Thread 2 completely overwrites the work of thread 1 because both threads made their calculations based on the exact same initial outdated state of the shared memory. An entire increment operation just vanishes into thin air, leaving us with a totally incorrect 51.
Section 3. Formalizing the chaos. Let's give this problem a name.
Now that we've seen the mechanical why of this problem and how assembly-level instruction overlap totally breaks shared memory, we need to formalize this chaos. Software engineers have very specific terminology for what we just witnessed. As defined here, what we just looked at is formally called a race condition. This happens when multiple processes access and manipulate the same shared data concurrently, and the final outcome depends entirely on the chaotic interleaving of their execution order. It absolutely perfectly describes that literal race to be last that we just saw. And it turns out the specific place in the code where this shared memory modification happens is called the critical section. If a thread is executing lines of code that manipulate entirely private local data, yeah, that's totally fine. But the very moment it touches shared memory,
like our x variable, it enters this highly sensitive danger zone. The critical section is exactly where race conditions happen.
Section 4. Rules for a solution. How to tame the shared memory chaos. So we have identified the root of the problem, the critical section, and we understand its weapon, the race condition. The final part of this explainer is definitely the most important. How do we actually tame this shared memory chaos? How do we build a foolproof solution? Well, for any synchronization solution to be considered valid and correct by an operating system, it must absolutely adhere to 3 strict rules. We are going to build them out one by one: mutual exclusion, progress, and bounded waiting.
The first rule is mutual exclusion. Simply put, at most one process can be in the critical section at any given time. Think of the shared memory as the Prime Minister. Only one person is allowed in the room to meet the Prime Minister at a time. Now, we could just write a naive, infinite while loop to block everyone from entering if someone is already inside. But if implemented poorly, this creates a horrible solution where nobody gets in and the entire system permanently freezes. It becomes a total deadlock. Let's move to and see how this builds. To fix that freezing issue, we have to add rule number 2, progress. If no one is currently in the critical section, and multiple processes want to enter, the selection of who goes next cannot be postponed indefinitely. At least one process must be allowed to enter. Mutual exclusion prevents the collision by saying at most one, while progress prevents the system freeze by saying at least one. Finally, we add the third piece, bounded waiting. Imagine a process finishes its work in the critical section, steps out, and then immediately jumps right back into the critical section before any other waiting process gets a turn. That's essentially scamming the system, right? Bounded waiting ensures there is a hard limit to how many times a process can re-enter the critical section if others are waiting. This prevents a nasty scenario called starvation, where a waiting process literally never gets its turn. And this brilliantly illustrates how these 3 rules act in perfect harmony. Mutual exclusion ensures exactly one process enters. Progress ensures the system always moves forward without deadlocking. And bounded waiting ensures fairness, so everyone gets a turn. Together, they force order upon the assembly-level chaos, making sure our variable increments from 50 to 51 and safely all the way to 52.
Which leaves us with this incredible realization. We just saw how a single basic addition equation requires 3 absolute, strict rules of synchronization just to execute correctly on shared memory. So imagine the device you're watching this on right now. How does an operating system manage millions or even billions of these microscopic critical sections every single second across multiple CPU cores without instantly crashing into a chaotic race condition? It's an absolute marvel of modern computer science, for sure. And understanding this assembly-level trap is your very first step to seeing how the whole shebang actually works. Thanks for learning with me today, and keep exploring.